estimation and prediction problem for stochastic systems. And by the end of the lecture today, I'm going to talk about just the expectations for the coming couple of weeks and also the exam. So in going over or reviewing what we did last time, I rewrote the problem formulation. So let's revisit the problem that we are considering in these lectures, the lectures for this week and next week, towards the end of the course. So what we are considering is the following: two processes, x of t and n of t, which we refer to as the signal x and the noise n. We also assume that the sum x plus n is equal to y, and that sum is somehow either observed or measured. So we measure y, but we want what? We want to estimate what x is. Okay. So we will determine the best estimate of the value of x at time t1. So this is the problem. Okay. We have noise, we have a signal we are interested in, but we are measuring the signal being corrupted by noise as y, and we would like to estimate x. So there are three cases or three scenarios. First one is what we call smoothing. What we call smoothing. So smoothing here is when we are interested, when the signal is at time t, right? X of t at time t, and what we do here is we make use of the copies of x or instances of the state x at t, t minus 1, t minus 2, t minus 3, or past values of x and the current value. That will give us smoothing. So what we call smoothing, which is when t is less than t1. Okay, so so t is that point there. Filtering is when we make use of the states, the state of x up to t. So past values of x up to t. So there is no. So in that case, what we are doing is filtering. Prediction is when we want to predict the next instant of the state x. So we have the state x up to t, but we want to predict what x is as t plus 1. So prediction, as we would expect, is to predict the next step. Filtering is to estimate what x is as t. Smoothing is we take all the instances of x and smooth them in a previous step to the current one. So these are the three states, but we are mainly focusing on filtering, but maybe we'll also go and consider a problem or two for prediction. We will see, but mainly what we are doing in these lectures is filtering. So let's dig deeper here, and so let y be the set of observations which are available to estimate x at t1. So in this case here, we have two cases, because we for discrete time processes, t is a set of integers. So t here, which defines the sequences x and n, right, is the one that determines whether we are dealing with a discrete or continuous process. So t is a set of integers, and y is simply a vector in this case. So we have y, which is a vector of elements, right? It has a y at t0, y at t0 plus 1, up to y at t. For continuous time process, y is a function. defined on the interval from t0 to t, right? So in that case, t is continuous, and y is no longer a vector of elements that has a stacks of that is stacked by its elements, but it's rather a function defined on the interval t0 to t. All right, so let y belongs to a set capital Y and X belongs to a set capital X, then a formal definition for an estimator, also known as an interpolator, also known as filter, also known as a predictor. Sometimes these things are used interchangeably, okay? Estimator, sometimes called filter, like Kalman filter, right? Kalman filter is nothing but an estimator, okay? So filter, sometimes estimator, interpolator, predictor is a function which maps y to x. So the formal definition of the estimator is a function that takes y and spits out x, or estimate of x. All right, the value of this function for a particular value of y is called an estimate and is denoted by x hat. It's denoted by x hat. To describe the problem completely, we must specify three things, okay? To specify the problem of estimation completely, we must specify three things. Number one, we need to specify what the signal is and what the noise is. I know the signal is not measured and the noise are not measured, but we need to come up with an understanding or assumption of what they look like. What are they, all right? So we have different options or different cases. Either the signal and noise could be continuous, could be discrete. They could be described by their covariance functions, spectral density. They could be described by a stochastic difference equation or a stochastic differential equation, right? So we need to know somehow what is the model of x and n, right? So that's something that we need to come up with. The second thing we need to do to find the estimator of the system, we need to define a criterion which defines the best estimate. Okay, so you need to find a measure by which you would say, oh, I got my estimate, right? And that criterion basically is the one that you will minimize in order to find your estimate. And in this case here, there are also many possibilities. One way is to define a loss function, call it B, like what we did in last lecture, which is a real function. Okay, so but this is very important. This loss function should have some properties. Number one, it should be a real function with the properties. It's positive, semi-definite, and symmetric. Bx is equal to b minus x, and b is non-decreasing for the positive argument when the argument is positive. Okay. Actually, these properties are general property for any cost functional that you would like to minimize, right? And typically they are satisfied when b is an integration of something. When b is an integration of something, typically these properties are satisfied, but with some caution right there. So loosely speaking, yeah, that's the case. Okay, so the loss is then the stochastic variable. Then the loss once you find your criterion, that's the loss function b, then the loss is then the stochastic variable b of x minus x hat, or b of x tilde, right? Which is we call it the estimation error. So b is a function of the estimation error. And the best estimate x hat is the one which minimizes the average, right? The average of this cost function or loss function. So notice that I use interchangeably the name loss function or cost function. Both are the same thing, okay? Loss function or cost function. And we would like to minimize it. And last lecture, actually, we showed that the best estimate, or the best estimate x hat, is the one which minimizes the average loss, this one, right? By by taking the derivative with respect to x hat last time and equated to 0, we got x hat, and we found that derivative of b, and we found that the expected value of b of x tilde is the one that does that. Of course, there are other ways to define the best estimate, right? Other ways than this one here, but this one, the one that we are is the most common one. There is also the third thing. So in addition to defining what the process is and what what x and n are modeled by, and also defining the criterion by which we estimate the x state, we also need to define the restriction on the admissible estimators. The restriction on the admissible estimators. By this, I mean maybe the estimator can be required to be linear, right? Maybe there is a requirement that the estimator has to be linear, or maybe it has to have some other spectral properties, okay? So if any, right, there could be no restriction. So then in that case, we don't have this third condition. Any questions so far? All right, so this is the problem, and this is the expectation, right? So the problem is this one, find x hat based on this equation. And for that, we need three things, right? We need to define x and n. We need to define the criterion, and we need to define a restriction on the estimator, if any. All right. So going back to what we did last lecture, right? So last lecture we talked about the minimum square error criteria, also known as minimum variance estimator. So last lecture we showed that using the mean square error criterion, the mean of the estimation error, the expected value of the estimation error is equal to 0, right? Based on this, the best estimate, or the estimate of the mean square, is equal to the expected value of x given y. All right, so this is what we did last time, and we showed that if I have an estimator like this, right, this is the estimator, then in that case, the mean of the estimation error is equal to 0. Right. Let's now continue with this one. Let's now see what the covariance in this case is. We showed that if the estimator is this, we have this. Let's see what the covariance look like in this case. So the covariance matrix of x tilde can be written as, we call it Rx tilde. And in this case here, I don't want you to be confused with covariance matrix and covariance function. In this case, both they are the same. They are different only in the case of continuous systems, when the process is modeled by a continuous differential equation, right? Or sorry, continuous stochastic differential equation. But in this case here, covariance matrix is the same as covariance function, especially when we're dealing with a vector case, when x tilde is vector. All right, so Rx tilde, Rx tilde is the covariance of x tilde, right? Which is equal to expected value of x tilde transpose. And knowing here, of course, that the mean of x tilde is 0, so that's why we have that. I can also write this as the expected value with respect to y of the expected value of x tilde transpose given y. So this is called the conditional mean with respect to y of x tilde. So these two are equivalent. All right. So now I want you to consider what's known as the trace of the covariance matrix. So the trace of the covariance matrix and the definition of a trace of a matrix is the sum of the diagonal elements. All right, so let's consider the trace of the covariance matrix. That means it's the trace of the expected value of x tilde transpose, right? The trace and the expected value are interchangeable. So you can take the expected value outside and take the trace inside. These are one of the properties of the expected value. All right, so you can get the trace inside. So you have now the expected value of the trace of x tilde transpose. Now, notice something, that the trace of x tilde transpose, where x tilde is a vector, this is also based on the properties of the trace of a matrix, it's equal to the x tilde transpose x tilde. So you switch the x tilde and x tilde transpose, so then you'll have x tilde transpose x tilde, right? And that is by definition the norm squared, or the L2 norm squared, or the Euclidean norm square of x tilde, right? And that's by definition the sum of the elements of x tilde squared. Okay, so have that. Please interrupt me at any time if you have any question. All right, so so based on this property here, right, the trace of this vector x tilde times x tilde transpose is equal to the norm squared. So then in that case, the expected value of the trace will be the expected value of the norm squared, right? Which is based on this one, the expected value of the sum of the elements of x tilde squared, okay? The expected value can go inside the summation, so we will have that. And the expected value of xi squared, the elements of x tilde squared, are nothing but the variance of the variance square of the matrix of x tilde. All right. So where I tilde is the ith component of the n vector x tilde, and sigma squared of x tilde is the covariance, is the corresponding covariance or the variance square. All right. Recall that the conditional bias base cost function can be written as this. So the cost function, or the loss function that we defined last time, right? So this, we did this last time, and we showed that the b of the mean square of x hat given y is equal to the expected value of the norm squared given y. So we did this last time from last lecture. Okay, so see last lecture for that. So we showed this, all right? Then now I need you now to compare this. So this is 2. I need you now to compare 2 with 1. We showed that the trace of the covariance is equal to the expected value of the norm squared. Now we're from last lecture, we showed that the loss function, or the cost function of x hat given y is equal to the expected value of the norm squared given y. If you compare these two, then you will see that the cost function of x hat is equal to the conditional expectation with respect to y of BMS is equal to actually nothing but this one here. Based on that one, right? Based on this one here, right? Which is equal to that one, right? So this is equal to that one, which means, so this is equal to that one, which means now that if you see here, the trace is equal to the expected value of the norm squared, which means that the loss of function, or the cost function of the mean square cost function of x hat is nothing but the trace of the covariance matrix, which is the sum of the variances squared, right, of the individual variances of the random variables xi tilde. So this is a third most important result here, in addition to these two results here. The first one is that the estimator is given by the expected value of x given y, and we showed that for this one, the expected value of the estimation error is equal to 0. Now we are saying that the the loss function, the cost function of x hat is equal to the trace of the covariance matrix. So the criterion, the one that we chose, the cost function based on the mean square estimate of x hat, is actually nothing but the sum of the variances of the estimation error, right? As we showed here. What does that mean? Well, remember that we got this x hat by minimizing this one. Okay, from last lecture, we got this one by minimizing this cost function. So now we're showing that this cost function is the sum of the variances of the individual estimation errors at each particular time, right? So that means that when we minimize this one, we minimize the variances of the estimation error at each instant of time. That's why this estimator is also known as the minimum variance estimator, right? So this is why we call this estimator at equation 0 here the minimum variance estimator, because we show that we show here that the loss function is nothing but the sum of the variances, right, of the covariances with the variance square of the estimation error at each instant of time. Any question? Any questions so far? All right, let's continue. All right, so from 0, right, from the estimator equation here, right, so this is the expected value of x given y. We can also write it as the integration from minus infinity to infinity x fx given y with respect to x by definition, right? So we have that. From this, so this is the estimator. This is the equation of estimator, right? So if we want to find x hat, we need to do this. We need to do either this one or that one. But this is not computationally convenient. This integration in particular is not computationally convenient because the conditional density function of x given y is not generally easy to compute, right? So if x given y, right, is not easy to compute. Let's do something about it. Okay, let's see if we can simplify this. So now consider the density function of fx given y. I can write it this way: fx given y is equal to fy given x, right, times fx over fy, or in this case, fx given y times fy is equal to fy given x times fx. So this is a known property of conditional density functions, right? Based on this, then I can write this integral here, this one, number 4, as x hat m of s, ms, sorry, mean square of x hat is equal to the integral from minus infinity to infinity x fy given x fx, right? I just substitute fx given y by this. So fy given x times, so here I have y given x, right, times fx over fy. Okay, so I only substituted here fx given y by its equivalence here, and I got that. Now, what is fy? Fy is the integration from minus infinity to infinity of fx and y, the joint probability density of x and y with respect to x, right? Which is the same as fy given x times fx with respect to x, right? Fy is equal to fy given x times fx with respect to x. So use that, substitute it back here, right? Substitute it back there, you will end up with this equation here. the x hat m mean square x hat is equal to the integration from minus infinity to infinity x of fy given x times fx over fy given x times fx. So for this one, in this form, we need what we need here to. So I need you to compare this one and that one. For this one, I need fx given y. For this one, I need fy given x, and I need fx. Both are, generally speaking, easy to find. So let's see if that's the case. Let's consider an example. Let's consider an example to see if that's the case. So this example here, find the mean square estimator for the scalar parameter x based on the scalar observation y is equal to natural logarithm of x plus n, right? So we have this equation here, and we want to estimate x based on the mean square using the mean square estimator given by this equation, right? And n is noise, where the probability density function of x is equal to 0 when x is between 0 and 1 and 0 otherwise, and the probability density function of the noise, or n in this case, is the exponential from with the power of minus n when n is positive or non-negative and 0 otherwise. Okay, so these are two given, right? This is one of the conditions in order, remember that to find an estimator, you need three things. You need to find what n and x can be modeled by, like this one here. And you want to know, second, the criterion. In this case, we are using the mean square criterion estimator. Third, if there are any if there are any restrictions on the estimator, and there is no particular restriction here, so no restriction here. Okay, so so now we need to use this equation here to find the estimator. So for that, we need to find, first of all, let's find the denominator. The denominator, which is fy, right? Because we just said that the denominator is fy here. So, so the denominator, which is also equal to fy, right? Let me put it here like this. So it's f given y of y given x times fx, right? Right. Okay. So what's that? Fx is given, right? And see here. Yes. So fy given x times fx, which is fy, right? So what is that? So that is, if you look here, because fx is 1, so we're going to multiply by 1 from 0 to 1. So the integration will be from 0 to 1, okay? And then we need to find what is fy given x. So fy given x, this is nothing but, so I'm going to write it here, this is equal to f n of n, right, in terms of x and y, right? So what is that? So this is e to the power of negative n. And what's n? N, so it's e to the power of negative n. And n is equal to y minus L, natural logarithm of x. So where n is equal to y minus ln x. Okay, so which means, so from here it's e to the power of negative n, which is e to the power of negative y minus ln x, right, times 1 from 0 to 1. Okay, if you use MATLAB, yeah, you can use MATLAB for this, or you can do it by hand. But if you use MATLAB, you will see that when y is non-negative, it's going to be e to the power of negative y over 2. When y is negative, then the limits of integration will change from 0 to y to e, and the result of the integration will be e to the power of y over 2. Okay, so that's that. Either this one or that one. Now, let's find the numerator. Numerator is x times that, right? And so the numerator, again, it's in this case here, it's from 0 to 1, right? X times that we just did, right? Which is this one here. So again, you just take that multiplied by x, right? And then do the integration. If you do the integration, it's going to, you will see that it's e to the power of negative y over 3 for non-negative y, and e to the power of 2y over 3 for negative y. So we have the numerator and denominator. Now divide them by each other, divide them by each other for this one to get that one. And you will see, so for example here, you can divide e to the power of negative y over 2 over e to the negative, divide this one, e to the power of negative y over 3 by e to the power of negative y over 2, then you will have 2 over 3 for y non-negative. That's the estimate of mean square. If you divide the other one when y is negative, then you have one has a power of 2y, that's the numerator, and denominator has a power of y, then you will end up with, in terms of y, so 2 e to the power of y over 3. Okay, one thing to notice here, so this is the estimator, right? This is the estimator for positive y and for negative y. And so the estimator here, there's something interesting here, which is if you see this, so this is the estimate of x. Notice that the probability density of the probability density, sorry, the x here has a range between 0 and 1, and because the probability is 0 otherwise. So we would expect x to live between 0 and 1, right? And the maximum of x is actually 1. That's the maximum that x gets. Now, the estimator is telling us that the maximum of x hat is 2/3, because the maximum of e is 1, so we have 2/3 out of these two ranges. So the maximum of x hat is 2/3, even though x belongs to 0 and 1, or the x has a maximum of 1. What does that tell you? Well, that tells you that the estimator is not perfect. The estimator here is not perfect. It will never be perfect because the estimation error will never be 0. The estimation error will never be 0. Actually, the estimation error will have a minimum. The minimum that the best we can get here is 1/3. Estimation error 1/3, which is 1 minus 2/3, right? So it's not perfect. Okay, something to, this tells you that the estimation for stochastic signals is not an easy, it's not an easy thing to do. Okay, because of the randomness of the signals. Any question?
Dr. Booker?
Yes.
I have a question. Like, can you go back to the previous page? Here, when you want to calculate like these two, like the integrals, like when you want to find f y given x, y given x. So like when we want to calculate f y given x, we assume that we know x. So x is a deterministic number, which is like natural natural log of x. And then so like in the formula, y is equal to a constant number, which is ln x, plus that like n, which is a stochastic process. Then how like, so like the density of the y would be equal to the density of that stochastic process, which is n, but how that constant x comes in? Like I didn't get like how you find out the fy given x.
Okay, yeah. So if y given x, right, is equal, so this one here.
Probably previous page we.
Yeah, but this one, if y given x is actually based on here.
Exactly.
Based on this equation here, right?
Exactly.
So y given x is the same as, it's the same as yeah.
Can you bring that page again, like the one that we have y is, yeah. So y is equal to ln x plus n. N is stochastic, and in a given x, like the ln of x is like some constant number. It's not stochastic anymore. So
yeah.
Y is a stochastic process with like a constant plus a random variable. So the PDF of the y is equal to the PDF of the random variable is equal to the PDF of the random variable plus that constant. That's that part.
So yeah, the result here will be random too, right? It's not going to be constant. It's constant, yeah, but it's random, right? Because it depends on x, and we don't know what x is. X could be anything.
Okay, but if the ln x is a random variable, then finding y is something like the PDF of y would be so hard. Like PDF of y is equal to the summation of two random PDF. I mean, that's you cannot simply say it's equal to the PDF of n then. I think the reason that you simply say the PDF of y is equal to the PDF of n is you assume that in given x, ln x is a constant. But I just don't get like how that doesn't involve in the PDF of y at all. Like you directly say PDF of y given x is equal to the PDF of n. Like you completely forget about that constant and then bring it in that integral. That part confused me. I didn't get it.
Okay. So what we are given is the PDF of x and PDF of n. And we are not given a PDF of y. We are not given the PDF of y. What we wanted, we want PDF of y. So PDF of y is given by this equation here. Now, for this equation, this is given, which is 1, all right? And so this is the one that we, if we can get this one, we solve the problem.
Yeah.
So what is this? That this is the PDF of y given x. So PDF of y given x. PDF of y given x can be found from this equation. So if you take ln x as to the other side, so I have 1 minus ln x. If you take the PDF of that, that would be the same as PDF of n, right? And yes. So I think that your assumption is correct. In that case, if we consider ln x to be deterministic, then it's basically PDF of y given x. That case, then it's which is the same at y, and then it will appear here. So your thinking is correct, but where is the what is this thing that is not making sense for you in your thinking?
So like I understand that when you say when you want to calculate PDF of y given x, it means that at one instant x, which means ln x is a deterministic number. But
it's given, yeah.
So like right now, let's say we have forget about this thing. We have y equal 5 plus white noise. How can we find the PDF of y? Is it like the PDF of white noise, or if it's like like what I'm trying to say is that, like, let's say y is equal to a constant c plus like normal 0 and 1. The PDF of y is normal 0 and 1, or is like that 5 should add it to the mean and like not happen anything to the variance. So like the PDF of y would be 5 and the variance of the next one, like the n.
So if this is constant, y is equal
Yeah.
to c plus n, okay?
Mhm.
So that means n is equal to minus c, right?
Mhm.
So PDF of y of n is equal to the PDF of y minus c, right? The left hand side is equal to the right hand side, and this is the same as PDF of y given c. So what's wrong with this sentence, with this equation? It's the same thing. If you know C, you know this one, which is the same as that one.
Yeah.
Think about it, okay? And if I have I will think about it. If I have another way to explain it, I will get back to you, okay?
Okay.
Yeah, where C is given. Where C is given.
Like the only thing like confuse me, like when you have y is equal c plus n, let's say n is a normal with mean 0 and variance 1, okay? And you
Yeah.
want to find the PDF of the y. C, because that the c is a constant, you can for sure say that, okay, the PDF of the y is also a normal. You just need to find the mean and the variance.
Yes.
The variance would be equal to the variance of the n, which is 1. But the
Yes.
mean would be c plus 0, which is c. So
Yes.
like the PDF of the y change is not PDF of n anymore.
No, yes, but we're not saying that this is PDF of y. We are saying that there's a difference between f of y and f of y given c. These two are not the same. What we're saying here is y given c. We're not the same. See, remember here, look here, look. F of y is totally different than fy given x, right? They are related by this equation here, so they are not the same. So fy is not the same as fn here. We're not saying that. We're saying that fy given c is n, f is f of n, but not, we're not saying fy is equal to.
I see. So I think I understand. The second question, very quickly, like how did you distinguish between, like in the next page, not this one?
Yeah.
Here, like from 0 to one integral is from 0 to 1, the other from 0 to e according to the y, if it's y positive and y negative. The thing is,
for the go ahead.
The integrals are for x, and x is always from 0 to 1, so never can go from 1 to e.
For that one, I don't have an answer for that, especially so this one 0. I got this from the book, and I'm assuming that the book is using MATLAB to do it.
Gotcha.
So I don't have an answer for this one. Okay.
I see.
Yeah. Good questions. All right. Any other question? Okay. Let's continue.
One more quick question.
Yes, go ahead.
So, like, generally, in this question, we wanted to find the estimate of x, and then like, so at the end we say, given y is greater than 0, x should be 2/3, and if the y is less than 0, the x should be something like this. Because like, as I understand from the estimation, we don't have the x, but we have the y. We see the y and s. So like seeing observation of the y here is not like a constant y. It's like any y greater or equal to 0, that will be the estimation of the x. And any y less than 0, that will be the estimation of the x. Correct?
Yes, correct. Yes, yes, yes.
Okay.
Yeah. This is the only thing that we measure. Y is we measure, or we are assuming that all the time y is varying, right? But we measure it. We know its value all the time. Okay, so that's the estimator. Okay, but we don't measure x, of course. Okay, let's summarize this. Summarize what we did so far. So how are we doing with time? Let's see, time is, I still have time. Okay, so theorem. The proof of this theorem is in Ostrom's book, the Stochastic Control Theory. It says that assume that the conditional distribution of x at t1 given y has a density function which is symmetric around the conditional mean. So m is equal to, which is the expected value, is equal to x times fx given y with respect to x, okay? And non-increasing for x larger than or equal to m. Let the loss function be symmetric and non-decreasing for positive arguments. Then the best estimate is then given by the conditional mean x hat is equal to the expected value of x given y, which is equal to the integration of x f of x given y. So what this theorem says is that if y has a density function which is symmetric around the conditional mean, right, and non-decreasing, this is first condition. Second condition, if the loss function be symmetric and non-decreasing for positive arguments, then the best estimate is the one that we just dealt with, right, which is the expected value of x given y, or based on this integration, or based on this integration here, which is the same as that integration there, right? So what's remarkable about this theorem is that it does not specify what the loss function is. Regardless of the loss function, right? Regardless of your choice of the loss function, the best estimator is always going to be the expected value of x given y, right? This is a general theorem. It's more general than what we proved or we showed in the lecture, the last lecture, right? It's a more general. Why it's more? Because we did not specify that the loss function is the mean square error function, right? So this theorem says that it implies that if the conditional density satisfies the conditions of the theorem, and the choice of the loss function is irrelevant as long as it is symmetric, as long as the loss function is symmetric and non-decreasing for positive arguments, right? So if the loss function satisfies these two conditions, then this theorem applies. Okay, so that's why this theorem is very powerful, and you can use it regardless of the loss function that you choose, as long as it satisfies these conditions. Any question? So this is just a generalization of what we just discussed. All right. Okay, let's consider another example. So in this one here, it's a Gaussian linear mean square estimator for scalar random parameter. So in this case, let's consider the following observation for a scalar parameter x. So x is a scalar, right? And I is I'm assuming now that we're dealing with a discrete yes, we are dealing with a discrete process, not assumption. It's a discrete process, right? And each time we are measuring y, right, for a different ni, where ni NIs are independent and lean and identically distributed normal random variables or noise with mean 0 and variance sigma squared. And so this is the first part of the first condition, which is we need to identify or specify what n is and what x is. The second part is we need to assume, or we assume in this problem, that x is also Gaussian with mean m0 and variance sigma 0 squared, right? And variance sigma 0 squared. So, so we have a number of measurements from 1 up to capital N of this yi, right? And each time we have this. And x is a parameter, is a scalar parameter x, right? Okay, so the problem is asking us to find the mean square estimator of x. Find the mean square estimator of x. So let's see the solution. From 6, sorry, not 6, right? 6. So this is question number 6. We are calling it question number 6 here. This is question 6. Okay, write 6 in a vector form. So if we write this in a vector, then y is equal to matrix H times x plus n. Notice that even though this is in a vector form, x is still a scalar. So you have, let's see something here. All right. So H is a vector of 1s, right? And y is a vector of y1, y2 up to yn, capital N. And n is also a vector of n1 up to n capital N. So now, instead of performing the direct integration in 5, like in this equation, like what we did in the previous example, right? We are going to solve this problem in a different way. It's because n and x are assumed to be Gaussian, okay, are given to be Gaussian, then it's easier to make use of the fact that the density functions are Gaussian for both of them and can be completely determined by their mean and covariance matrix. So let's see how we can do that. Let's first find the PDF of y, the density function of y. So the density function of y, let's, for that, it's going to be Gaussian, right? And so for that, we need to find the mean and covariance. So the mean of y is the expected value of y, which is the expected value of the right-hand side here. So it's the expected value of capital Hx plus n, which is the, and h can go outside. So it's h expected value of x plus expected value of n. The expected value of n is given as 0. So we have h m0, which is the mean of x. So this is the mean of y. It's equal to h m0, which is the mean of x. Covariance of y is equal to the expected value of y minus its mean, because y is a vector, so we have y minus its mean times y minus its mean transpose. So now substitute by y here. So so it's the expected value of h times x minus its mean plus n minus its mean, which is 0, all right, times that transpose. So I can simplify now this one. By this one, I can take h outside from the right as h transpose, and from the left h, and then you have expected value of x minus m0, expected x minus m0 transpose, plus expected value of n transpose. How I did that? I did that because we used the fact that the NI sequence is white noise, okay, which means that their mean are 0, and also we assume that the NIs, the sequence NI and X are uncorrelated. So there is this assumption that the NI and X are uncorrelated, which means that they are independent, which means that the expected value of X times N is equal to 0, right? So based on that, we can simplify this equation to this equation here, right? And then you can see here that this equation here, so the expected value of x minus m0, this is by definition the covariance of x, which is given, right? Or by assumption. By assumption, it's not given. By assumption, it is sigma 0 squared. Sigma 0 squared. Okay, so and because it's a scalar, I can get it outside. So it's sigma squared, sigma 0 squared h times h transpose plus the covariance of the noise, and the covariance of the noise is also given here, which is sigma squared. So we have sigma squared times I, where I is the identity matrix. All right. So now we have the mean and the covariance. Based on that, we can define the density function Fy as Fy of y is equal to some constant k1 e to the power of negative half y minus its mean transpose times y, because everything is a vector, so we have to be careful here because we cannot divide by the covariance, so we need to multiply by the covariance. This is, remember, this is a matrix, so this is matrix, right? Covariance of y is a matrix because y is a vector, so we need to be careful here. So I was gonna write it here in the denominator, but that's wrong. Okay, so you have to write it as a matrix. So this is sigma, so write this one, sigma 0 squared h times h transpose plus sigma n squared I inverse, right, times y minus h m0. Yeah, so this is transpose this. Yeah, so I have that. Right. So this is I'm applying here the definition of the Gaussian function. I'm assuming that, not assuming, it's actually obvious, right? So you have a Gaussian process here, Gaussian process, or a sequence, Gaussian sequence here. So y will be Gaussian, right? So that's why, in order to define what the PDF of y is, right, we need to define the mean and the covariance, and then apply in the definition of the Gaussian function or Gaussian PDF, and where K1 is a normalizing, we don't care about it too much now, constant. Okay. Now let's consider next. So this problem is a little bit long, so bear with me to get to the final objective here. So consider next the density or the conditional density if y given x, y given x. Okay. First thing we need to do here, everything will be Gaussian. So so we need to find, in order to find that. So this is the nice thing about when dealing with Gaussian functions or Gaussian processes, that in order to find everything, you need only to find the mean and covariance, because we know exactly the closed form of the Gaussian distribution. All right. So in this case here, we need first to define the expected value of this function, which is the same as the expected value of y given x, right? Which is equal to expected value of y, which is h of x plus n given x, right? And actually this one here, it's nothing but h of x. All right, and the covariance, will be r y given x is equal to the covariance of y given x is equal to the expected value, all right, of y minus the expected value of y given x. So this is by definition here. Times its transpose, y minus expected value of y given x. The whole thing here given x. Okay, so take a minute here and look at this. So the covariance y given x. Okay, so it's y minus its mean, and the mean is here, right? This one of them is transpose, so this one is transpose. Okay, y minus its mean times its mode given x. Okay, so by direct definition of the covariance of this one, of the conditional covariance here. So this is equal to, so let's now substitute we found that this expected value is h of x. So this is equal to the expected value of y minus h of x times y minus h of x transpose given x, right? And this is equal to what? Anybody? Can anybody tell me what this is equal to?
Is this covariance of n?
Why? Why is that? Why is that, Ali Reza?
Because like I think
yeah, it's correct, but why?
like I
Similar
think y
to
give
what? Yeah, go ahead.
similar to we discussed like in my
Exactly.
earlier question, I think.
Yeah. It's similar to our discussion earlier, right? So this is y given x. Going back to the equation, very important. Going back to the equation, here's the equation. If we know what x is, then PDF of y given x is the same as PDF of n. All right, so this is the same as expected value of n transpose, right? Which is sigma n squared identity. Okay, now we combine these two results with the known f of x to obtain fx given y, x given y is equal to fy given x, y given x. Sometimes we don't need to write this one, actually. The book is using it, so that's why I'm using it. But you can also just drop this one here, the subindex here, and just write it fy given x. So, a little bit. okay, times fx of x over fy of y. Okay, so this is that, right? So we know this is given. We got this, we got that, so we got everything here, right? So let's see. So the whole thing will be k, all right? So this k is just a normalizing factor. How am I doing with time? Just have 5 minutes. So I'm gonna write this one, and then I'm gonna complete the next lecture. Let me write this. Okay. So we know this, we know that, we know that. So what is this? This, we got this. Where did we get this? Well, y given x, we know its mean and we know its covariance. So that means it's minus half, okay, y minus hx transpose, right? Y minus its mean, and the mean is hx. Now I'm writing fy given x, right? Times or over its covariance. And the covariance here is, because it's scalar, I can write it as sigma n squared, right? Times I, right? So I will be multiplied by y minus hx. So this one here is, okay, so we know that this is fy given x. Now what is fx, right? So minus fx is given, right? Did we get fx? Oh yeah, fx is by assumption. So let's do it. So it's and this is because it's scalar. So it is. I can write it as 1/2 sigma 0 squared x minus its mean, right? The whole thing squared, right? Because it's a scalar, so I don't need to multiply transpose by transpose, right? And then because now, so this is because now the denominator, so it will be a positive power plus fy, and fy has a mean of hm0 and has a covariance of this one here. So it's going to be a rather big one. So I'm going to write it here. So that would be half y minus hm0 to the whole thing transpose times the covariance, which is this one, covariance, which is this one, inverse. So the covariance inverse. So that would be sigma 0 squared h times h transpose plus sigma n squared I inverse times y minus h m 0. So the whole thing here is the power of the exponential function. All right, so I'm going to stop here, and I'm going to give you, to complete this example next week. I'm gonna show you. We know this, right? If x given y, we can also write this if x given y based on another definition that it will include the estimate. So let's see here. Yeah, I think my time is up. So I'm gonna finish this next lecture. Okay. So in the last, so I have 1 minute just to say a couple of things. Number one, I'm going to post a homework for this stuff, based on this stuff, probably today or tomorrow. And the exam, the final exam, I just checked today, and the final exam is going to be May 8th which is Friday, from 10 to 12, right? So I'm going to give you more specifics about the exam next lecture, but it's going to be similar to exam number 1, which means you will be given like probably 24 hours to do it on Friday, May 8th. All right. That's all what I have. Any questions? All right. Thank you very much. See you next lecture.
Thank you.
Yeah. Leng Shao, do you have any question? Oh, yeah. There is also another project or homework that I uploaded to Canvas. It's I have given you a number of papers, and I would like you to choose one paper. Let me know your choice as soon as possible so that no two can choose the same paper. And I would like you to give a presentation, PowerPoint presentation about this paper, like for maybe 5 minutes on May 6th, I believe, or the last lecture in the course. And then we'll follow it by question and answers. So what you need to do is you need to see if you can find a concept, if you can simplify or explain a concept that is related to what we are studying in this course here. The paper can also, you can choose a paper from your own research or something that of your choice. You just need to let me know about it. Okay, and this is regarded as a homework like any other homework. Okay. All right. Thank you very much, guys. See you next lecture.